I'm Rahul and I'm participating in the cecc3 contest that is organized by the TAs of MITx, and my project is on an object counter. And in front of you is the list of the materials that is required to make the object counter. And starting from the this first one, that is 4510, is the BCD counter, that is binary coded decimal counter. The 7447 is a 7 segment decoder, that is a common anode decoder. That is, if we feed into it the binary coded decimal input, then it will give output as a 7 segment display for the 7 segment display of type common anode. Then this is the 741 IC, that is a very familiar IC, and it is as famous as the 555 timer IC. And this is the op-amp that I'll be using for the comparison purposes, that is as a comparator. The mode will be as a comparator. Then there is a sensor, that is this LDR, that is the light dependent resistor. Its resistance in the light decreases, that is in the darkness its resistance is very high, nearly some mega ohms, and in light, if we throw light on it, then its resistance decreases. Then there is a potentiometer. I have written 3 values, any one can be taken, but the 100K will be preferred because potentiometer will be used as a potential divider to feed into the op-amp, that is 741. So 100K will consume the least power because very less amount of current will be drawn if we use a 100K potentiometer. Then comes the resistor, that is a 10 or 100K kilo ohms resistor, that is this. After that there is a 470 ohm or 330 ohm resistor, that is we will need 2 of them. I have used a 7 segment display, that is this LED display, which is a common anode type. For recognizing common anode, we can go and see that is CA is referring to the common anode. We will need a breadboard, that is this, a breadboard, then a few jumper wires, in fact many of the jumper wires, and a white LED. Now I'll tell you a great method that I have discovered of recognizing the white LEDs. If you see from the top, you can see a greenish color in the top view of this LED. That is a peculiar property of the white LEDs. I'll show you another LED which is not white, of some different color, and you can see there is no such color. You can see that there is no such color, no greenish yellow color is there. But in the case of white LED, that is this is the greenish yellow color. So having discussed the materials, now I will be going forward towards the schematics and the circuit diagram and the approach how to make this object counter. Well, this object counter is very simple, and if we go according to Professor Agarwal, that is going by using the power of abstraction, we can really build this very easily, very nicely. The concepts will be explained, and that will be a great experience to everyone. So after knowing the materials, we will start on with the schematic, and I'm going to show you the abstraction or the system approach. In this, the whole system will be built by breaking into subsystems, and after that we will make each subsystem will be dealt individually, and after that we will join the subsystems and the whole system will be built from that. Okay, so watch out. So there are 3 systems. The first one is the input. That will comprise of the sensors which will take the input from the physical world and will feed itself. The data which will come out from this input module will be fed into the next subsystem, which I like to call as the processing part, or the process. This is the processing. We will get the input from the input input modules like the sensor. In this case, LDR is the sensor, and then it will be processed by an IC, and in this case it will be 4510 BCD counter, and that processed information will be shown in the form of output, because processed information is a form which is electrical in nature, and we humans need some kind of stimulations like light or sound to understand what's the result. So this is the output. We have talked about the three things. So our attention will be now on this input part. First we'll design the input, then we'll design the processor part, and finally the output part. So the input will comprise of an LDR sensor, and because LDR is an analog device and the processing is easier always in the digital domain, so we'll convert that analog data into a digital one. We are not going to use any kind of professional ADC or something like that, but it will be an analog to digital conversion in a very crude form. We'll be using a simple device that was discussed in the course, that is the op-amp. In this case, this is pin number 7, that is the VCC one. This will be the ground input, so we will give it a ground. This will be the power input, so it will be the power, that is 5 volts. I am using 5 volts, so I'll be labeling it as 5 volt. Then this is the output. So before I bring into it the sensors or the LDR, let me discuss a part of this op-amp, that is op-amp used as a comparator. So op-amp is a comparator. We know that this basic equation of op-amp is known to all of us, that is V plus minus V minus. This equation is known to all of us, where A is a very large quantity and this is your V out. Okay, so if I give a reference voltage to this, that is V ref, and this is V in, that is the V input, and this is the V ref. So what will happen is, the output that we are going to get is, it is V in minus V ref. That will be your V output. It is this output will be A times V in minus V ref. So we are now ready to understand that how it will be comparing two voltages. So in this case, we will compare this input voltage to a reference voltage, and if input voltage is greater than the reference voltage, my desired output should be 1, and if it is less, my desired output should be 0. So this is the summary of what we have discussed now. That is, if V in is greater than V ref, we get a high logic that we label as 1, and if V in is less than V ref, we get a low logic that we label as 0. So this thing can be inferred from this figure that was already explained in the lectures. So an op-amp has a very high gain, that is A is very high. So A is very high, and because of this, even if there is a small change, that is, even if V in minus V ref is a very small quantity, its V output, the resulting quantity, that is V output, is very large because of the value of A. But it cannot be indefinitely large. It can only go till the supply voltages, that is the positive supply and the negative supply, that is, this is the range. So if this is the case, that is logic 1, then we get something like this, and if there is logic low, that is 0, we get output value like this. So this is the case where op-amp was considered completely linear. So, and for our purposes that will suffice, because we are trying to evaluate it as a digital device, means the output will be used for a digital device, so minor variations won't affect. And that's the specialty of the digital devices. We know it, that digital devices are very immune to noise. So what to do is, we will take the supply, negative supply, as the zero potential, that is the ground potential. So this figure will be modified as to this level. So the zero will be not the zero, that is the logic low level, will be the ground, that is the 0 volts, and the logic high will be the 5 volt that we are going to give in this case. So after this, we will try to design the whole of the circuit. We'll use a very familiar circuit, that is of the resistor the voltage dividers of the resistors. So I use a potentiometer, that is a resistance, that is a voltage divider, and this is a variable resistance with terminal coming out like this, and I will feed it into the negative of, that is the V minus, that is the inverting input of 741, and of the output from the LDR will be fed into the positive part of this IC. So this time I change the config, I just flip over the IC a bit, that is, I will flip over this op amp a bit. So here will be your VCC, or the the positive supply, and here I will be taking as ground. I'll ground it rather than giving it a negative supply, and I will connect this to this level, this thing, and this will be also grounded. So it will behave as a potential divider just by rotating this thing. In fact, the potentiometer we are using is a kind of rotatory device, and the resistance depends on the rotation, the angle of the potentiometer. We will rotate this thing, and its position, relative position, will decide how much resistance this variable resistance will offer. And if we can use it as a potential divider, just like this. Place it like this, and connect this to positive one, connect this to negative one, and just by rotating it, this thing, we can get the required voltage or the potential difference. So I have zoomed in so that you can see the value printed on it, that is the 100 kilo ohm potentiometer, and we'll rotating it through here. Okay, now I will take out the next module, sorry, the next thing, that is next component, that is the sensor, and that will be an LDR. So what I'm going to do is, this is also a variable resistance, and I will model it like this. This is the light source which is falling on it, and as the distance of this light source increases from this, the resistance will fall, the resistance will rise up, and as light source is coming near to it, it means more light intensity is there, its resistance will decrease. And I connect 100k resistance, and I give it and connect the remaining end to the ground. So this is also a potential divider, this is also a potential divider. So there will be some voltages here. So I call it as V in and call this as V ref. This is the V in and V ref, and then here is the V out. So the V in is there, the V ref is there, and the V out is there. Our equations are also there with us, that is V in minus V ref into A, and this is equal to V output. With all these things in hand, we have our input built up. So what will happen is, as we set this to a particular position, that will be our V reference. Suppose I set it into the halfway, that is the angle which I rotate the potentiometer is half. It is not half in degrees or radians, but suppose if I rotate this thing into a position so that it is in the midway. So if I rotate it to the half, that you can see this pointer is at the half, and means it is halfway away from both the other ends of this potentiometer. So this will offer a resistance half of 100k, that is 50k. So what will happen here is, and this will be 50k and this will be 50k. So this is 5 volt is coming at this point, and 50k resistance, will divide it as 50 by 100 into 5, that is 2.5 volts, and this will be V ref. Okay, now this LDR is set, this is 100k. Whatever will be the resistance of this LDR, let us call as R LDR. Now 100 upon 100k upon R LDR plus 100k times 5 volt will give us V in. If this value is greater than this V ref, if V in is greater than V ref, we get a V output that is nearly 5 volt or the high logic. If this V in is less than V ref, then we get a low logic or 0. So seeing the equation, you can easily understand that if this light is brought nearer to it, that means if RLDR is decreased, then the value of V in will increase. That means if light is brought closer to it, then there will be a greater chance that you will get a higher logic, logic 1 on this V output, that is nearly 5 volts at this V output. It won't be exactly 5 volts because we have ignored a lot of other things, but that will suffice, that will do, that will be, this approximation will be sufficient for us, and we can consider it safely as logic 1. So if we bring it near to this V in will rise up, and the moment it goes above than this V ref, we get a high output here, that is V out is high. When we take this torch away, that is if it goes behind, then this resistance increases. So from this you can easily judge out that V in will decrease in that case, and the moment it goes below V ref, V out is logic 0. So this is what I have shown you on the paper and using a pen and paper. Now we will do a kind of simulation so that you can get convinced by this. So we are now going to simulate it on a software, and the software's name is Proteus, and this software is available from Lab Center Electronics. To find it out, go to Google and type Proteus and you will get this. The latest version is Proteus 8. I am using an older version because I am more comfortable with it. So the main device in our input mode was 741 IC, which was the op-amp, and we also need some resistance, along with resistors we need an LDR, we will also need an LED to see the output. Well, in the real world we will not use this LED. This is just for showing the simulation that we are correct. So this is IC741. The data sheet is this, with these are the pin connection diagrams. So we are using a dual inline package, so the pin connection is something like this. We will not care about pin number 8, pin number 1, pin number 5. We will only consider 7, 6, 4, 3 and 2. So the 7th pin is the positive supply and the 4th pin is the negative supply. So 4th pin, in my case it will be ground, and the 7th pin will be the positive input, positive supply voltage. The second pin is the inverting input, or the V minus as in our equation, and pin number 3 is the non-inverting input, or the V plus, or the V. Here in pin number 3 will go in our V in, and in pin number 2 will go our V reference, that was V ref, and 6th pin will act as output pin. Okay, I am going to take an LDR. I rotated it for my convenience. I'll change its properties as 100 kilo ohms. The 7th pin will be connected to the power, so I have connected it here. I'll need a potentiometer as well, so for that I'll select it, and this will be the potentiometer. For giving the power, we use the inbuilt power mode, and the ground will be connected like this. So as I have explained you already in the pen by using pen and paper, that the connections or the schematics, so it looks a bit ugly, but never mind. I hope that you can understand how the connections are made. So the 6th pin is our output pin, so I take an LED. A resistance would have been required if we were not simulating it and using it in the real world, but as this is a simulation, so we don't worry about the LED blowing off. We can directly use it here. Now everything has been set, and let's simulate it. Okay, if I go up, you see the LED is now glowing. It's a bit tricky, you might not be getting a feel that how it glowed up, so I'm now attaching the probes. In this case, this is one probe, this is the another probe, and the third probe is the output. So you will see here the voltages. If this V in is greater than this V ref, so let's label it. This will be V in, this will be V ref, this will be V out. So simulation, you see, and when V in is greater than V ref, we get a V out that is 1, that is a high. Okay, you might be surprised that the value of V out is 2.29. It's because this LED is offering some amount of resistance, but it's not offering infinite resistance. Now I will show you one more thing. If I remove this and if I now simulate it, you see the voltage is quite higher. In the other case it was less than this 4.01 when I used an LED. So I'll use the LED again. I'll get it back. You see the V in. See the V in, as the V in went down, the V ref, as soon as the V in went down of V ref, the V out is now in a low level. So I'll increase the V ref now. I'll change V ref in fact. So this is, I am increasing V ref now. The V ref is less than V in, and hence this LED is glowing. I hope that you have understood the input part, and now I'm going to discuss the processor part. The heart of the circuit, or the main processing part of the circuit, was the IC4510. This is a 16-pin DIP, that is 16-pin dual in package IC, and this IC is a CMOS IC. So here the power supplies will be labeled as VDD and VSS, for DD for drain and SS for source. So this is the pin diagram of the IC CD4510. I'll explain you how this works actually. The preset enable works. The first pin, that is the PE, its full form is preset enable. So until unless it has a 0 input inside it, till then this whole counter will function. Otherwise, if it is given 1, then it will go to a preset value. Q4 is the most significant bit output. We'll not bother about P4, P1, P2 and P3 now, and we'll not also care of CO, that is the carry out pin. This is the carry in pin, and we have to give a 0 input here so that counting can start, otherwise there will be no count. So it must be given a 0 value. Q1 is again the least significant bit. Then VSS should be connected to ground. Reset pin should be given a 0, otherwise the values at Q1, Q2, Q3 and Q4, those are the outputs, that will be always 0 irrespective of whatever we give as input. Then up or down counter will select that whether you want to count up or count down, that is whether you want to count from 0 to 9 or from 9 to 0. Then Q2 is the second most significant bit, Q3 is the third most significant bit, CLK is the clock input that will be given to this 4510 from the input part, and this will help in counting. This is an edge triggered IC, so this will be quite accurate. Edge triggered means it is triggered, or a count is increased on the edge of a clock, not on the level. This is level, this is rising edge, and this is falling edge of clock. So CLK is clock. So I think you have understood this. So I'll now discuss the schematic, how the connections are to be made so that you can understand it much in a better way. So what I do now is I got the input signal, and this time I won't be making the diagram exactly according to the pin diagram given here, but I will do it according to my convenience. So this will be the clock pin, then there is a preset enable, there is a carry input, then this is VSS. uh, Let me mark them here, VSS and VDD. These are the power inputs. So here we will give the positive one, and here we will give the ground. So this is the clock, this is the preset enable carry input. Now we are left with the up and down. This will decide whether to count up or whether to count down. If we give it a 0, then it will count down, and if we give it 1, it will count up. So it is left now. I think everything is done. So here will be the outputs, that is Q4, Q3, Q2 and Q1, and this will go to the output, which we will not care now. We will focus it in the end. Preset enable, as I have mentioned earlier, preset enable should be given a 0, so this should be connected to ground. Then carry input should also be given a 0, otherwise counting cannot start. This will also be given a ground. Oh, I forgot one reset pin, so I'll include that as well. So this is reset, and this should also be given a ground. Up and down counter must be given a high value, otherwise if we want to count up, so I am counting up from 0 to 9 because this is object counter. So in certain applications you might want to count backwards, but in this particular application I want to count up, so I am giving it a high value. And as I will give clock input like this, my counting will go on. So now in a simulation I will show you how this is going to work, and you will get a better feeling, and I hope that you will like it. So we are now ready for the simulation, and I'll be simulating it again in the Proteus. So we were discussing about the processor part. For that we need an IC which is numbered as 4510. This is the binary coded decimal counter, BCD up and down counter, you can see it's written, and it's a CMOS IC. CMOS IC means less power consumption. This complementary metal oxide semiconductor field effect transistor is being used in this, and for generating the clock signals, that is for testing purposes, I'll be using an SPDT, that is single pole double throw switch, SPDT switch. So I won't connect the processor part with the input for the time being. I'll first test it individually, and then after satisfying everyone, after convincing, I will connect it to the input. So this is the SPDT. I connect it to the clock. This is the data sheet for 4510, and this is the pin diagram as I have shown you in the notebook. So in this case, instead of writing VCC, we write VDD and VSS. VSS for the ground terminal and VDD for the positive value of positive supply voltage. So it is similar from the MOSFET. In the MOSFET case, there was a drain and there was a source. You can understand from that. So I will show you a table which is very important. uh, this is the truth table for this IC. From this truth table, the whole circuit can be built very easily. You can see that until unless we give the carry input pin logic 0, there is no counting, and until unless we give a preset enable 0, then also there is no counting. Until unless we give a reset pin 0, there is no counting. So preset enable, reset pin, and clock input, carry input, sorry, carry input should be given 0. These three pins should be given 0. And for up and down counting, as I have told you before, we have to give a logic 1. And on the rising edge, there is a up counting that can be seen from this diagram as well, that when the clock is rising, that is, you see this is the clock rising, and this is the Q1, that is the least significant bit, it goes up. And this is the timing diagram of carry in up and down, and this is the clock so this is the timing diagram for clock input, and this is the timing diagram for the output pins. So we'll go back to the simulation. We have to give a 0 input to this CI pin, to this preset enable pin, and memory reset pin. So for that, I take a ground terminal and connect it to MR, PE, and CI. This up and down must be given a high. So I have connected it as such. Now the another part of this switch is given a ground. So when the switch is thrown upwards, we get a logic high into the clock. When the switch is thrown downwards, we get a logic 0 into the clock. Now we will go to the 4 outputs. So for that, I have to use LEDs, and as usual in the simulation I am not going to use any resistors, but in the real world simulation, in the real world actual breadboarding or actual circuit making, we have to use a 330 ohm or a 470 ohm resistor, because otherwise the LED will be blown off. So I'll consider it as the most significant bit, and this is the least significant bit. So I'll name it as it is given there, that is, it is connected to Q1, so its name is Q1. Now we need to give a common ground to all. So we are ready for the simulation. Press the play button, and presently we have given a low input to the clock. As soon as I throw the switch upwards, you will see a number is displayed here. This LED will glow. You see, this LED has now glown up. Now again I will throw it down, then there will be no change, and as soon as I throw it up again, Q2 will glow. These 4 are representing the BCD. The binary coded decimal is represented by these 4 LEDs. So you can see it again. You see, this is now 1 0. Then the binary representation, the BCD representation for 3 is 1 1, that is 0 0 1 1. So you see, so for this is now convincing to all of you, I think so, and this is representing 4. Now I'll be using a BCD display, that is a BCD to 7 segment display, and you will be seeing exact natural numbers, you will be seeing the whole numbers, that is from 0 to 9 will be displayed on that 7 segment. That 7 segment has an inbuilt decoder, that is from binary to 7 segment LED decoder. So in simulation we are having that, but in the real world I'll be using another IC which will decide the output. So I take another device named as segment. This is the 7 segment binary coded decimal display. This can display the binary code directly. So this is the least significant bit, and this is the most significant bit. So, and starting from 0, we see that is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0. Now, till now we were working with a switch which was connected towards the clock. But now I want that this input should be now given to the clock, so that you'll get a better feeling that how this object counter is going to work. So I stop the simulation and I remove this switch and I remove this. I give it to the clock and I move this whole lock above. Okay. So now I'll be simulating it again and you'll see how the circuit will actually be working. So I get it back and I get it ahead again. You see a count has increased. I get it back again and I get it forward. So this is saying that if light intensity is increased, then from darkness, if light increases, then a count will go up. Similarly, what we can do is, because in simulation I cannot bring some object which is obstructing the path of this light, in the real world demonstration I will be showing you that bringing something in between the light source and this LDR will increase, uh, uh, bringing something in between the LDR and the light source and removing it after that will increase one count here in the binary coded decimal display. But there is still one more step to go. We have to design the output as well, because in the simulation I was having a 7 segment display which can directly display from the binary coded decimal, but we need a decoder such that this binary coded decimal can be decoded into the 7 segment display. Okay, so we will now discuss the output part of this whole system, that is, this will be the output subsystem. So the output subsystem is the display. We are counting the objects, our target is counting the objects, so we have to display it certainly by some light indications. So here we are going to use the 7 segment display, that is the 7 segment LED display. So this is the 7 segment display. It looks like the number 8. The 7 segments are labeled as A, then this is labeled as B, C, D, E, F and G. So these are labeled as such. Now to drive this LED we also need a decoder, that is a digital IC, and since I am using a common anode, this is a common anode 7 segment display. This is a common anode 7 segment display. So I'll be using a 7447 IC for this purpose. See, this 7447 IC will drive this LED, this 7 segment LED, and so this is the pin connection diagram of the 7447 IC. So as you can see that B, C, A and D are the inputs for this IC, and these are the outputs, as I have already mentioned you in this. This was the common anode 7 segment display, and this is the IC which will be controlling the number which is displayed on this. So what we have to do is we will feed the output of the processor part, that is 4510, into the A, B, C and D. That is, the Q1 will go to A, similarly Q2 to B, Q3 to C and Q4 to D, and this will be fed into the 7 segment. So whatever binary coded decimal we get an equivalent numeral printed on this thing, that is the 7 segment LED. Now I'll explain you that how the both of them will be joined. So again I will draw a diagram, and certainly the pin connections won't be as given here, it will be at random. So these are A, B, C, D, E, F and G. I take the 7 segment display and this is suppose my common anode. So suppose this terminal was for A, then this is for B, similarly for C and so on up to G will be connected. So this was the G, this was A, this was B, this was C, D, E, F and G. These are the 7 segments, and there is also a dot for the decimal numbers, but we will not light this up. We will be considered only with this. So now I will like to show you one 7 segment LED so that you can get a better feel of what it is. So this is the 7 segment LED, and this is the common anode which can be recognized from this CA. So now how these are joined. So you can see the different terminals of this 7 segment LED. So there are 5 terminals, 1, 2, 3, 4 and 5. So the middle one is always the common anode terminal, because this is a common anode type 7 segment LED. This is the dot. This dot is representing this terminal is for this dot, which will represent the decimal digits. And from above you can see that this is A, B, then C, D, E. Instead of having directly here F and then G, it is G and F. This was a bit confusing for me, and it can be the same story for you as well. So having discussed the pin diagram of 7 segment LED, and so now we are ready to simulate in Proteus, and this was the place where we left. So I am removing this part. Now we'll need one more IC, that was the 451 that was the 7447, and this is it. We'll also need a 7 segment display. So the 7 segment display is, we need a common anode 7 segment display. So this is the 7 segment common anode display. Now we will place it. So this is the IC, and the common anode 7 segment display is this, and the connections are very easy now, as I have shown you it in the paper. I will show you how it responds to BCD. I'll generate artificial BCD, that is without using the IC. I'll be generating it. For that purpose, I will use 4 SPDT switches, which will represent our 4 most significant four significant bits, 4 bits. Suppose this is the first one, second, third, and fourth. We'll give the power and ground terminal to each of them. So now we will simulate it. Okay, we'll first go and visit the data sheet, because it is an important part. See, there are 3 more pins which I have not discussed yet. That is the lamp test. This BI means blanking input, RBO means ripple blanking output, and RBI means ripple blanking input. So we'll refer to the truth table of this IC. This is the truth table for this IC, and seeing the truth table, you can infer that, you see, if we want some logical outputs, that means if we want the desired outputs, our desired output is from 0 to 9. We will not bother about 10, 11 and 10 to 15. 4 bits constitutes from 0 to 15 in decimal. 4 bits, that is 4 binary digits, constitute from 0 to 15 in decimal. So this that is 4 bits will constitute from 0 to 15, but we are using binary coded decimal, so it is from 0 to 9 only. So we'll be bothering about from 0 to 9 only. You see, the lamp test is always given a high, then only we are getting a desired output. Then the ripple blanking input, that is RBI, is don't care, but in the first case, that is if we want to display 0, we must give it high, otherwise we are not going to get the desired outputs. Next, we must give the blanking input as well high, otherwise we will get all the pins high, that is we will always see that we will not see anything, because it's a common anode display, so we will not see anything. When there is a low into the pins, when there is a low into the terminals of the 7 segment LED, then only that particular segment glows up. For this case, that is for the 0 case, you can see that it is L means low, that is A, B, C, D, E and F all are low. G was the middle segment, that is if middle segment is not glowing, then it will represent a 0, otherwise it would have represented 8. So middle segment was given a high signal, so this will represent the number 0, and similarly you can infer from this truth table. So this was important for us to discuss. That means all other we will give as high. So as discussed, I'll be giving the lamp test, this blanking input or ripple blanking output, and ripple blanking input a high. Okay, so going back to Proteus, I'll give them a high signal, that is I will connect them to the power. So well, this is a common anode, so I'll connect this as well with the power. This was the terminal for common anode. Now I'll simulate it. You can see that all is 1, so I put it into ground first, that is the input is now 0. See, the output is coming 0. Now going back to the data sheet, now I will go according to data sheet. Suppose I want to represent number 5, that means I have to do the input C and A as high. So here my A is this, my B is this, my C is this, my D is this. Let me label them so that you'll be more comfortable with it. So this is the simulation. I have to give the input as, in this case I'll have to give input in case of 5 as C is high and A is high and other two are low. So C is high and A is high. You see the output is 5. Okay, and suppose if I want to get an output as 9, so I'll have to give D as high and A as high. So I'll give D as high and A as high. So the output is 9. Well, the representation of 9 is like this, and this particular segment doesn't glow in case of 7447 because it is designed as such. And you will also see the 6. I will show you the number 6 as well in this. That is C and B are high. That is C and B are high, and see this is 6. So the same thing will appear in the real world as well. Now I'll connect this to the processor part. Instead of giving input from SPDTs, I will connect this to the processor part. So that will help you to understand, or you'll better understand it. So the outputs are connected to respective terminals, and this is to be connected to the high pin. Well, I have to give it a power because it's a common anode. So I start the simulation, and this is 0. So yes, that's 1, that's 2. So our project is complete on the simulation, and that was the best part of this, that first I have designed it on pen and paper, then I have divided the whole system into subsystems, simulated each system, then finally connected all the systems together, and this was the final system. The complete system is in front of you now, and now I will breadboard this, and I will show you that the output on the breadboard. I won't show you how to join the wires because I think that will be a wastage of time, so I will show you the demonstration directly, and I hope then that you will certainly enjoy it. And what I feel is that I have used the knowledge of this whole course, that whatever Professor Agarwal has taught, whatever the TAs have taught till now, they have shared with us. The knowledge which I gained from this course was tremendous, and I have used this knowledge in designing and building this whole of the system. Well, I have been working on microcontrollers from a long time, but since the because I wanted to do justice with this course, hence I have used only these ICs and all, and without using any kind of C programming or assembly language programming. I have tried to make this only using the ICs, and I think that anyone watching this video can easily make this system, and the system is really enjoyable because you can use it to count the number of people coming into your house, or number of bottles passing through a conveyor belt or something like that. So let's go and see the demonstration on the real world. Well, this is the completed system, and in front of you see the object counter that I have prepared. Well, the connections look bit ugly, and I'm sorry for that, but never mind, I'll still try to explain you how they are connected. Well, in a breadboard These two lines are known as power lines, and from these power lines I am drawing power from an external power source that I will show you after a while. So this is the first part, that is IC741, and so you see a notch here, and the counting of pins starts from here. That is, pin number 1 is here, pin number 4 is this, then pin 5, 6, 7 and 8. So I have connected this wire. You can see this is towards the positive terminal. I have taken this one as the positive line and the lower one as the ground line. So this is pin number 7 and this is connected to the positive terminal as was mentioned in the data sheet of IC741. Then the output from the potentiometer is connected to pin number 2, and the output of the potential divider that is built from this LDR and this resistor is into this pin number 3. Pin number 4 is grounded, and you can see this is ground, and the same ground is connected to this potentiometer. Well, this is the LED, the white LED, and this is a 470 ohm resistor connected to it. It is connected so that the LED will not be destroyed or damaged due to high current flow. So this resistor will limit the current flow. This is pin number 6, and from pin number 6 is going the output towards this processor. The processor is getting the clock signal, and this is pin number 15, that is the clock signal of this processor, or the IC4510. And I won't go into detail of these connections because I have already shown you in the simulation and in the schematics have been discussed before. So well, I'd like to tell you that this is a resistor that I have connected to the common anode. This is so that a less amount of power is consumed by this 7 segment LED. Otherwise a high current will flow through the 7 segments and LEDs could get destroyed, and it would also be not good, because if LEDs are not destroyed even, then too it will consume a lot of power, and so the rest of the circuit will get short of power. I have also connected one LED that I previously said that I won't connect it, but I have connected it so that whenever I pass anything between this white LED and this LDR, you will come to know about it. So the power source that I have taken is this, and here, and as I was not having a battery for that moment, so I have used a power source, and you can see that is a 5 volt and ground is there. So I'll be connecting the breadboard wires there. So this one is ground, and this one is the 5 volt. And so we are ready for the demonstration now. And so you see a 0 number being displayed on the 7 segment LED. Now I obstruct the path of this. You see a count has increased. Again, when I obstruct the path, you see the condition of red LED, that is blown off. Again, when I will remove it, it will glow again, and the count will increase by 1. You see, the earlier was 1 and now it is 2, and similarly it's 3, it's 4, it's 5, 6, 7, 8, 9 and 0. So if I'm passing an object like this, it has counted 1, it has counted 2, 3, 4. So as the objects pass through this way, a count is increased in the 7 segment. So I hope that you must have enjoyed it, and you might be liking this, because this is something that all of you can build, and the parts are very cheap. I don't think that in Indian rupees it will cost more than some 100 rupees. It will be less than that. If I include the breadboard, then it can go at max at 150 or something, 150 rupees. So this is a great thing, and I inspire you that everyone who has done the course of edX 6002X should try this once, must give it a try. And that's all. Thank you.